The key concept in question 12 is obviously to know the geometry. Can we set up a relationship between the components that they provide us? But that's going to lead us to algebra that looks something like this. Okay, it's going to produce, somebody said earlier, exponents were in it, so I just guessed and maybe got it right. When you have exponents that are greater than 1, okay, so what I want you to understand is that when I have an equation that looks like this, 2x plus 3 is equal to 12, maybe equations that we've set up before in this class, there are still exponents there. There's an exponent, it's an understood 1, right? Well, when your exponents are greater than 1, the number one thing you want to think about is factoring. That's the approach. Whether the exponent is a 2, a 3, a 4, doesn't matter. You're going to try to factor. And that's if you're at all interested in what you're going to see next year in Algebra 2 right now, it's strategies that are going to teach you how to factor x squared in the varying different formats that you might see there. It's going to allow you to maybe learn initially how to factor like x cubed and x to the fourth and x to the fifth. And then when you get to algebra, or you finish Algebra 2, you get to college algebra. Guess what college algebra is? It is every single topic that you talk about in Algebra 2. Okay, so college algebra is simply Algebra 2 condensed into 18 weeks, and we view things maybe a little bit differently or from a different perspective, but we do the exact same stuff you learned in Algebra 2. But it's basically 2 years that teach you how to factor. And that's not the only thing they teach you, but they help you develop that skill because of how necessary it is in trigonometry, how necessary it is in calculus, how necessary it is in a physics course. So we're developing the skills that are going to set you up to be successful in other courses. So when you see things that are x squared or x cubed or x to the fourth, and right now all we're going to see is x squared, you want to think about factoring, and you want to think about getting things equal to 0. Okay? That's how we're going to factor. But before we get to that, I want to think about this. Let's just say I give you a number. Let's say I give you a number 24. Okay? If I ask you to factor that, what is, when I say the word factor, we're looking for things that multiply together to give me that 24, right? So if I take 24, what's one number that I could use that multiplying it by something else would give me 24? Okay, 8. So 8 is a factor of 24. What I mean by that is that 8 will divide 24 evenly. Okay? What will I get back if I take 24 divided by 8? I get 3 back, right? Okay? So 8 times 3, or 8 and 3, are both factors of 24. So take 24 divided by 8, I get 3. Take 24 divided by 3, I get 8, right? Okay? So, what you did there, okay, is you factored 24. What's the only operation you really did? You started with 8, how did you get to 3? You did what? You divided, right? So when we see the word factor, it's just a fancy word for divide, okay? Likewise, when you see the word distribute, or the acronym FOIL, okay, what operation is happening there? What do you do when you FOIL? You understand? Not divide. If factoring is the inverse of foiling, okay? So if factoring is division, foiling has to be multiplication, right? You do first times first, outside times outside, inside times inside, last times last, right? So factoring and foiling are inverses, okay? They undo each other, and it's because factoring is division and foiling is multiplication, okay? That's kind of, if you understand that concept, that's what we're going to do with this thing, okay? We're going to see basically what divides that, okay? And it's going to be a binomial, so what binomial divides that to provide me a second binomial, okay? Now this link here, this tool, okay, because some of us aren't very good at this, right? Factoring, we're kind of bad, which is okay right now because you're sophomores and freshmen, and just your exposure to this stuff has been limited. So are you great at it? Probably not, okay? I used in the last class, if I'm a basketball player and I go to basketball practice and I'm just god-awful at shooting free throws, okay? And through the duration of basketball practice, maybe we do a little 5-on-5 scrimmage or something like that, and I get fouled one time. and I shoot a 1 and 1 and I missed the first one. Okay, I shot one free throw in the whole entire practice, right? So when I get in the game on Thursday or Friday or whatever, and I get fouled, and I sucked at free throws at practice, I shot one free throw and missed it at practice, what's the likelihood that I am successful in that game? Not very good, right? Okay, so convert that over to the classroom. If I suck at factoring, okay, and I do 1 or 2 examples in class in the 50 minutes that we're here, okay, and I can follow along. Maybe I'm successful at doing those. Maybe I'm not, okay. Is that going to make me better at factoring and make me successful when I get to the test? Or when that question shows up on the test, am I probably going to miss it, okay? Like I missed the free throw in a game, right? So that person that wants to make that free throw in the game, what do they have to do after practice? Practice. And they have to stick around and practice a little bit more on their own, right? They have to put in the extra time, the extra legwork to put up, 50 to 100 free throws, maybe every night, okay? So get back to the classroom. If I sucked at factoring, we saw 2 in class, what should I probably do when I go home? If I know I'm bad at it? Practice, okay? Now, I'm not saying do 100 or 50 every night. Maybe you do 5, 6, 7 a night. Maybe you spend, maybe you allot, hey, I'm going to do 10 minutes of this stuff tonight because I know how important it is for the rest of the things we're going to do in this course. And if I put 10 minutes in tonight, 10 minutes in tomorrow, 10 minutes the next day, that might be all I need to really get the hang of this, okay? But if you never do it, you're never going to get good at it, okay? So to find a place where you can do this, one, you could go to YouTube, you go to Google, type in factoring examples, all that kind of stuff. But if you go to my website, kind of already put all this in here for you. Scroll down below your notes and all that kind of stuff. And where it says factoring, click on factoring. Brings you to this. And there's a litany of videos here that you could watch. Okay. Now, I'm thinking probably right now, this first column is the ones that you would probably want to watch. The other ones are a little bit more advanced. I used to use the first column and the last column. The last column is similar. But this one here is a little bit more of a more advanced algebra type question, maybe even algebra 2. You talk about factor by grouping, but we'll get to that at some point in this class. But watch these videos because there's a lot of examples in there. So I can pull a video up, get this example. It says x squared minus 2x minus 15 here. Write it down, do it, work through it, hit play, maybe scrub through the video to get to where the answer is. If my answers match up, then I'm good, right? If my answers don't match up, I scrub backwards, I hit play, and I watch how they do it, and I listen to the explanation, okay? Or if you click on GeoGebra applets here, click on that. Okay, it's going to take a minute for this to load because I think I got like 6 or 7 applets here. And this is something that my college algebra students use as well. So there's some on here that maybe you would look at, and some you want. I think this first one's going to be the one that you're going to want to really kind of focus on. And it just generates an infinite number of trinomials that I can try to factor. Okay, so I just click that button. Now some of them are already factored, so that one's pretty easy. It's already done the first step for us. So I'm going to try to find something a little bit different. So I get to that one. And I want to factor this, okay? So I get x squared minus x minus 72. If I want to factor something, okay, for our class right now, when we apply this inside a picture, normally it's going to be an equation. We're going to have 0 over here, okay? That's really the only time that you can factor, is when we have a 0 over here and actually work down to get a numerical value for x. But as you're doing these, there's some things you want to go through. And this is not a direct or strict set of steps or things to look at, but I think it's always good to look at a GCF, see if there's the greatest common factors. For instance, if there was a 2 here and a 2 there, try to divide every one of these terms by 2. I would want to take that out. It makes the problem easier if I can do that. Okay, so I'm always going to look to see if there's a GCF. Okay, other times I'm going to look for kind of unique special cases for factoring. For instance, you guys remember talking about these last year, like x squared minus 16, or x squared minus 36, or x squared minus 9. You guys remember what those are called? What kind of numbers do we have here? What is 9, 16, 36? They're perfect squares, right? Is x squared a perfect square as well? Yeah. Okay. X times x, correct? So those are a difference of perfect squares. So I might look at special cases. That might be something that I want to think about as I'm trying to factor, because that should make things a little bit easier. Okay. We should know from last year this breaks down to x plus 4 and x minus 4, right? This goes to x plus 6, x minus 6, x plus 3, x minus 3, right? So the first one, the first special case, the one you're probably most familiar with, is when we have a squared minus b squared. It's a perfect difference of perfect squares. It will break down to the square root of the first object. So square root of x squared just gives me x, right? And then plus the square root of the second object. And then I have the same thing, but then I use subtraction between. Okay, so that's a special case. You look for those things. In this case, obviously, we don't have that. The next thing you're going to do is look to use what we call the product sum, either method, technique, whatever you want to call it, rule. And that's really what we're going to use here. The product sum method is I'm going to look for two numbers that multiply together, give me that number, negative 72, and add up to give me that number of negative 1. Is that okay with everybody? Okay. You can only use the product sum method if your A coefficient, which is the coefficient that goes with x squared, is a 1. Okay. Otherwise, you have to use another technique a lot of times called the A times C method, and we'll get to that later on when we need it in other areas. Okay. So let's use this product sum method. Okay. It says we're looking for two numbers that multiply together to give me negative 72, and they add up to give me negative 1. Okay. Now some of you might say, okay, what are these two numbers? Maybe I set up a chart and I say number 1 and I say number 2, and I say, okay, well I know that 1 and 72 will work. But if I do that, one of them's got to be negative, right? So if I make it negative 1 and add that to 72, do I get that one right there? Or negative 1? I get 71, right? If I make this one negative and that one positive, I get negative 71. So those are not the factors that I'm looking for. So then I try another factor. Well, 72, I know divided by 2, so maybe I try 2 and 36. Well, if I have negative 2 plus 36, it doesn't give me that negative 1. If I have negative 36 plus 2, it doesn't give me that negative 1. So I know those aren't the right ones. And then I try 3 and 24. And I know those aren't going to work, right? And I can keep doing that, right? That's going to be a pain in the butt the bigger that 72 is. If I look at 72, as you grew up in 5th grade, 6th grade, 7th grade, and you're doing these factors, what are maybe the first two factors people think about when they see 72?
8.
8 and 9, right? Okay. So if I go 8 and 9, and this is another thing to think about, if this number here is pretty small, you would say 1 is pretty small, right? Then that tells me the two factors that I'm going to need to multiply together to get this are close to one another. Does that make sense? Okay. Now they're negative, so I got 8 and 9 are the numbers that are going to multiply together to give me 72. But one of them needs to be negative, right? Is that going to work? Is negative 8 and positive 9 going to give me this negative 1? Or is this one going to work? Positive 8 and negative 9. So the way the practice here is that we take x plus 8 and then x minus 9, and that's equal to 0. Now, that's it, and I'm not going to get into the kind of the theory and why that product sum method works. It's really not that hard, but we talked about that in college algebra and why that product times with two numbers that multiply together, give me negative 17, add to negative 1, why that works. But for you guys, the way you can see if this works is I just said that factoring is the same thing as dividing, right? So if I divide something, so we go back to that number, I said 24 at the beginning, and Gage gave me 8 back, right? Or said 8 was a factor. So I take 24 divided by 8 and gives me 3, right? Well, to make sure that works, can I take 3 times 8 and get back to 24? So I can undo my division with multiplication. So we just divided a polynomial and got down to x plus 8, x minus 9, right? Can I multiply that back out and see if I get that thing right there? What's x times x? Careful. X to the second. When you multiply like bases, you add the exponents. So that's an exponent of 1, and that's an exponent of 1. So x times x gives me x squared. What's 8 times x? 8x, right? What's x times negative 9? Negative 9x, right? So I did first times first, outside times outside, inside times inside, and now last times last would give me negative 72, right? When you combine like terms, is that your negative 1x? So does it make sense that I know that this thing here is exactly the same thing as that? Okay. Maybe to give you a visual, when we deal with algebraic, this is going to give us, you guys remember what x squared's graph is going to look like? You remember seeing parabolas last year? If I go x squared minus x minus 72, I get a parabola that looks like that. I'm going to change the scale here real quick. Okay, so I get that parabola, right? Well, if I write that equation as x minus 9 times x plus 8, do you see it? The red curve goes on top of the green one? So does that prove to you visually that those two things are the same? Okay. So now the question is, how do I solve for x? Well, when I know what x is, when I know a value for that, x plus 8, excuse me, it just ends up being a number, right? X minus 9 just becomes a number, right? If I have a number times a number, and that's going to get me back 0, let's say I tell you that number is 12. What's this number have to be? It has to be 0. Good, Zach. Okay. If this number is 40, what's that number have to be? It has to be 0, doesn't it? If I'm multiplying two numbers together and I get 0 back, one or both of them have to be 0. Okay. So what numbers will do that for this? What is going to make this thing here 0? What x value will make this go to 0? Doesn't it have to be negative 8? What x value will make that thing go to 0? 9. So I can set up these two little equations and they'll get me those values of negative 8 and 9. And those are then the solutions that when I plug it in here, if I plug in 9 right there, what's 9 squared? 81. Minus 9. What's 81 minus 9? 72. What's 72 minus that 72 right there? If this is 72 here, right? What's 72 minus 72? It's that 0. These are the only two numbers that are going to behave like that to give me 0 when I plug it back in here. I get negative 8 squared. Negative 8 squared would be 64, right? Minus negative 8. Well, what's 64 minus negative 8? Yeah, it's 72. It's 64 plus 8, right? Well, 72 minus then that 72, does that still give me 0? All right, so that's what we're doing algebraically. So if you're working at home, you know, if I'm on this one and I work through it and I hit check factors, it gives me the x plus 8 and the x minus 9, right? I can go through another trinomial. I can try that one. What are the two factors that I'm going to use here that multiply together to give me 16 add it to 16? 6 and 10. Check my factors. 6 and 10. Try a new one. Two numbers that multiply to give me 14 add to 9. 7 and 2. Check it. Okay. So I think if you do that type of thing at home, you're going to get much better at the questions that you see inside Math Excel, because a lot of times, especially at this point in the course, they're going to periodically throw in systems of equations, periodically throw in factoring, periodically throw in maybe root equations. All right, and at this stage, they're assuming that you know that algebra, you've mastered that algebra, and you can move on. Okay, we've talked about this before. The end of course exam is really it's gauging what you get on that. You get a 2 or 3 or 4. It's telling you how good of a geometry student you are, right? But a lot of the things that get you to those geometry answers are a lot of preliminary algebra. And if you're bad at the algebra, there's absolutely no way that you can show somebody that you're good at geometry, okay, or on that test. So we need to make sure that we are comfortable with this stuff. So when we look at this problem here, this is question 12. They say in the directions that this thing is a rhombus. Okay, so now when we have that information in mind, it should allow us kind of to have a list of properties kind of appear to us. Does that make sense? And the hope is that we know all those properties kind of like the back of our hand. Maybe at this stage, because we haven't used them a whole lot, we don't, but hopefully we're still working on those and getting better at those. But if it's a rhombus, the first thing that it had to be was a parallelogram, right? Do you guys agree with that? And if it's a parallelogram, what would you tell me about that angle compared to that angle for a parallelogram? They're the same, right? Opposite angles of parallelogram are congruent, so those two angles are the same. Now, because it's a rhombus, this is the reason they told us it's a rhombus, is because we're now looking at that segment right there. What do you call that for a rhombus? Or any quadrilateral when you connect a vertex to a non-consecutive vertex? Say it again. I didn't hear you. Diagonal. Good. Okay. So that's a diagonal. All right. And when we talked about rhombuses yesterday, we said a diagonal of a rhombus is going to do what to that angle? What's it look like it does? It's going to bisect it, right? It's going to, diagonals of rhombuses bisect opposite angles. So those two angles are going to cut in half. Okay? Here's the argument. If this picture was just saying that this entire angle was 4x squared minus 27, and this entire angle was 3x squared minus 6x, obviously we set those two things equal each other and move on, right? We don't have right now a specific predefined theorem that says that angle right there is the same as that angle right there. But we can go through the use and the knowledge of this being a parallelogram, that being congruent to that. So let's say this angle here is 30 degrees. This one would have to be 30 degrees, right? Now I use the property that this thing's a rhombus, and that diagonal is going to cut that 30 degrees down to a 15, right? Is going to cut this 30 degrees down to a 15? And now what is the argument that I can say about those two things? They're equal, right? Okay. So, in a rhombus, that angle right there is going to be congruent to that angle right there. Okay. If you think about this, does that make sense? Let's take a rhombus. Let's look at this bottom rhombus. Do you know if it's a rhombus, do you know if that side's congruent to that side? I said bottom rhombus. I meant bottom triangle. If I know if that side there is congruent to that side right there, what type of triangle is this thing? If two sides are the same, it's a isosceles, right? And what do you know about the angles that are opposite congruent sides of an isosceles triangle? That angle there has to be congruent to that angle there, right? So this is actually a congruent isosceles triangle. So again, that tells me that that angle right there is congruent to that one. All right. So a lot of the stuff that we've learned in the past is present here. It works here. So we should set up the equation 4x squared minus 27 is equal to 3x squared minus 6x. Is that all right with everybody? Those two equations, those two expressions should be equal because those angles are equal. Now, this is where kind of that introduction to factoring takes place. I have an equation now that has x squared in it. Okay? Just like you guys know that if you get an equation that has x and y in it, you need other equations, right? But the way we write equations has a implied set of rules in it. Okay? And when I say implied, it means that I'm not directly telling you what to do, but I'm giving you hints, right? So if I say, no homework tonight, I really like this problem, I really know my properties for tomorrow, what am I implying? Quiz tomorrow, right? Okay? I'm giving you instruction, I'm giving you hints that there's something that you need to worry about, okay? So there's implied rules or directions inside 4x squared minus 27 equals 3x squared minus 6x. When you see that power of 2, the implied directions are to factor. All right? Last year, you get a worksheet in Algebra 1, and it has that on there, and it says in the description, factor this, right? Okay? That never happens in geometry. Okay? You never get a problem that says, do this algebra with it. There's implied rules that you have to understand. Okay? So when we see x squared, we want to factor. So when I want to factor, I want to get things equal to what? 0. Okay? So factoring, this is kind of what I think about every time I see powers of 2 or 3. I think that kind of visual. Factor, set equal to 0. Okay? So I'm going to get one of these sides to be 0, and I think that side probably makes more sense. So how can I get this 3x squared to move across the equal sign? Subtract it, right? So I'm going to subtract 3x squared. Now I come over here and I'm going to align it with its like term. Okay, so x squareds line up, and 4x squared minus 3x squared just gives me 1x squared, right? How do I get this negative 6x to the other side? Add 6x. Okay, so now I come over here. Is there anywhere that I can add 6x to? Are there any like terms of x over here, x to the first? No. So I just write down that I'm adding 6x to this left-hand side. The left-hand side so far is x squared. I add 6x to it. Does that give me 0 on the right-hand side? And that's what we wanted, right? But I also need this negative 27 to be there on the left-hand side as well. Okay. Last class we kind of talked about it this way. If I have 4x squared minus 27, I have 4x squared minus 27. I can actually write that. And that equation right there says the exact same thing that the blue one says. Okay? Because what's 0 times x? It's just 0, right? 0 times anything is 0. We don't usually write that. It's not really something that we are taught to write, but it is useful in some aspects. But it allows me to realize that there is a term over here that has x's with it. It's just 0, and 0 times x is 0. So we never write, 12 plus 0 or 4x squared plus 0 or anything like that. We just write 4x squared, or we just write 12, right? Adding 0 to it just gives it, 0 is what we refer to as the additive identity. It just gives me back what I started with. So if I have 4x squared plus 0, just write as 4x squared. But here I think it's maybe useful because now we see I can subtract that 3x squared, subtract that 3x squared. Now I add that 6x here, I come over here and I line it up here and I add it to that 0, right? So 0 plus 6 is that 6x squared that we need in our blue equation there on the right hand side. Does that make sense, everybody? Okay. One of the issues that I get with people is that they see a lot of x's and they don't know kind of how to combine those. You can remember you have to have like terms, right? Like terms is the variables have to match, and the exponents have to match. Okay. So we get down to this now. Okay, and this looks just like the initial equation we did in class, right? So what are two numbers that multiply together, give me negative 27, and add up to 6? Yeah, 9 and negative 3. Good. So we got x plus 9 and x minus 3 is equal to 0. So now these two numbers multiply together and give me 0. So one or both of them are 0. So x is equal to negative 9 or x is 3, right? Now, when you get multiple answers, and it's something you want to check every single time that you get multiple answers, especially if there's context to the question, meaning that there's a picture and there's other properties that exist that those answers cannot violate. Okay? Think about this, and I'll show you how to use this calculator to maybe do some of your algebra for you kind of easily. I want to take negative 9 and plug it in here to see what I get back as an answer. Does that make sense? So using this calculator, if you have this calculator, you can hit negative 9. And then this STO button stands for store. And then I'm going to store it as x. Okay, so it's just taking a variable. If you remember last year in Algebra 1, they would give you, like, this is an expression like 2xy divided by r, and then they say x is 3, y is 4, r is 7. Can you evaluate? You plug those things in and evaluate, right? It's the same thing, okay? Just x is now negative 9. Now I'm going to go type in 4x squared minus 27, hit enter, and it's going to give me that angle to be 297 degrees. Okay? And here is where we need to make sure that we understand what's going on here. We just said, by using negative 9 as a solution, that this angle here becomes 297, right? What is that angle right there going to be? 297, right? What is that angle right there going to be? 297. What is that angle right there going to be? 297. Does anybody see a problem with that? How many degrees should these 4 angles of my parallelogram add up to? 360. This 297 4 times blows that up, right? So what we have here is a solution that does not work. A lot of times we call that algebraically an extraneous solution. Okay, extraneous just meaning it's a solution that shows up through the procedure, but it does not fit the equation. It does not fit, I guess, the context of the problem. Okay, I'm going to try 3 now. Plug 3 in. So I'm going to set 3 STO x, hit enter. And now I'll just type in 4x squared minus 27. I get 9. Is 9 an okay angle measurement? Yep. I'm going to do the same thing for, I should probably do it for 3x squared as well. So I do 3x squared minus 6x. Gives me 9 back again. Just want to make sure it gives me a positive number back. So it's okay now that that's 9, 9, and 9, right? Because all you've done is eaten up 36 degrees, correct? So because I've only eaten up 36 degrees, do I have left over for that angle up there and that angle down there? Maybe I ask you what one of those blue angles is. Can I take 360, because that's what all 4 of them should add up to, right? With these 9s, I've used 36 degrees. So that's what I have left over for the blue ones, right? But what do you know? What's the relationship between the 2 blue ones? They're congruent. So what can I do with that? Careful. If they're congruent, you got 2 of them, and I know they add up to 324. Yeah, divide by 2, and it gives me 1 to be 162, right? So now I have all the angles that are necessary for that rhombus, okay, with that set of expressions for those angles, okay? We did, in the last class, we did 2 of those examples with that picture. You are going to, now we spent a bulk of the entire period on that question, right? Okay. What's that tell you about that question, Cameron?
It was hard.
Maybe not hard.
It took a long time.
We spent 50 minutes on it. It took a long time, yes. But what's that tell you about maybe your necessity for learning that? I spent 50 minutes talking about it.
Probably you should know it.
You should probably hold that question and that problem, that procedure in high regard, right? It's going to be important for us. We're going to use it, right? I tell my students all the time, and I tell you guys, maybe you've heard me say this, I'm not going to teach you something that you don't need, right? I'm not going to waste my time teaching you something that a year from now or 2 years from now you never see again, okay? I think that's kind of wasteful of time and kind of disrespectful in regards to your time. So I'm going to teach you the things that you need to know to be successful in our courses. That is huge. That is paramount. That's one of the most important things that we talk about throughout all mathematics is how to factor, okay? So please, please, please heed that warning. And as we go through questions, try to pick up on things. Try to pick up on hints and tips and procedures so that you can get a little bit better at factoring. Let me give you